Okay, let's get started, everybody. It is May 3rd, and we are in Module 3, talking about intermediate representations. So last time we started talking about ASTs. Today we're going to talk about them a little bit more. In particular, we're going to talk about how to create them. We saw how to create them with parser actions, and we saw if we were able to have a left recursive grammar, it wasn't so bad. But what we're going to see today is that in the grammar that we have, it's not left recursive, so we do need to think a little bit more about how to actually get an AST from our recursive descent parser, which is what you'll be doing next homework. On top of that, what we're going to do is we're going to talk about type checking. So this is an analysis that tends to be really nice to implement over an abstract syntax tree. So we're going to talk about some of the typing rules in the languages that we know and love, and then what we're going to do is talk about how to actually infer types and make sure that the types all make sense throughout our program. Okay, but as always, let's get started with some announcements. So, thinking about homeworks. So like I said, homework 1 grades are coming. We're aiming for Monday. We seem to be on track, so expect those. Homework 3 is out now, and I released a grammar.txt on Canvas that is essentially a solution for the previous homework. It's not the only solution. I saw that some people, did different things for homework 2, which is also fine. But this solution is in case you want to use it. I think it's quite a simple version of the grammar, so you can use that. It's the grammar, and it comes along with the first plus sets, and so you can essentially just implement that recursive descent parser the way we've seen in the slides the last few lectures. Homework 3 is due on May 9th. So we gave the extra time so that you'd have time to study for the midterm. That's coming up on Monday. So that's the next item. Midterm is on Monday. It's taken during class. You're allowed 3 pages of notes. One thing Ant mentioned to me is he says that he likes to take his notes. He likes to write them by hand because he says it helps him remember. Some people like that. Some people don't. I don't care if you print them off. Whatever you want. 3 pages of notes front and back, however tiny you want to make it. To study, I'd say study slides, study homeworks, and study some of the book readings. Like I said, if it's in the book but we didn't cover it in class, it's not going to be on the midterm. It's just we do end up following the book kind of closely for some of this, so it can give a different perspective, which is always good to help learning. There's 3 questions with multiple parts each on the midterm. As I mentioned, I will not be there, so Riddick and Sakshi and some of the tutors will be here to proctor. Shouldn't be an issue. Because we basically fill this room to capacity. So to give us a little bit of breathing room, I booked an overflow room, 106, which I'm pretty sure we're 105 now, so I'm pretty sure it's around here, although the campus can be kind of confusing sometimes. So I made a Canvas announcement on which room you should go to. It's based on your last name. Did everybody see that? Okay. So basically, if your last name starts with G or earlier, then go to 106. Otherwise, come here. And again, there's a very short quiz today that, I know you guys want to study. So the quiz is basically, do you know which room you're going to? So just please be aware of that. So the study guide, I'm just putting this in the slide so that you have it available easily whenever you want. The new update to it is, as I was refining the questions, what ended up happening this year is that we have no material from Module 3. So basically last lecture and this lecture will not be on the midterm. It's just everything before that. So essentially regular expressions, scanners, grammars, parsing, parse trees, stuff like that. Derivations, ambiguous grammars, how to avoid ambiguity, that sort of stuff. Okay, so that's coming up on Monday. Any questions on what we have coming up? Yep.
So I know, I was looking at one of the previous lectures. For the follow sets, we only look at the empty strings. On the midterm, should we be doing follow sets?
Just do it on the empty strings, because really, the follow set's defined for any non-terminal, but really the only reason you need them is to get your first plus sets, and that's the only place where they matter. Yep. And as always, if you run into anything like that on the midterm, any questions that you don't know, you can always just write down your assumptions, and that makes it easy for us to grade, and it makes it easy for us to give. Hopefully, when the assumptions are written down, if they're reasonable, we're happy to give full credit. Any other questions? Simon?
For the homework 3, would the test 3 has a greater sign and the grammar doesn't?
Oh.
Insert 1 into the grammar?
So you don't have to insert 1 into the grammar. You can put 1 in the grammar if you want. So maybe that's a good test case to make sure that you fail when you need to fail, and you can just make it a greater than to catch it. Yes, good point. Yeah. I was sort of just writing down some C programs, and that one slipped through. All right. Anyone else? Okay. In that case, let's go over the quiz from last time. So, for the quiz, first one, we've been talking about parse trees and abstract syntax trees now. Are they the same thing? Who says yes? Yeah, who says no? Yes. So the answer is no, even though they can look very similar. For example, we saw this last time, that if we had a simple grammar for this plus and times, you'd get a parse tree that could look like this, whereas the AST over here looks much simpler. Remember, the parse tree is defined almost entirely in terms of the grammar. The nodes are non-terminals. The leafs are lexemes. This is essentially tied to the scanner and the parser. When you move to an AST, your nodes are operators. Your leafs are literals, usually numbers or IDs. So it ends up being a lot more succinct. In some of our grammars, we saw that you end up getting these long sticks, and that's because we had these multi-level grammars. We did that to make sure that our languages weren't ambiguous. We did that to make sure that our languages encode precedence. And so your trees can, even for something simple like an input like this, in this case we have to put parentheses around the 1 plus 5 to make sure we do 1 plus 5 first. You can see this makes it so this left-hand side actually goes down pretty deep. But the AST is much simpler. Now, we still have the precedence in the AST, and that's important because the AST has meaning baked into it. Over here, we put 1 plus 5 in parentheses. That's how we got the precedence. Over here, the 1 plus 5 just appears deeper in the tree, so it's evaluated first. So that was one of the differences there. Okay, the next question about intermediate representations. So if you're writing a compiler that has M front-end languages and N target architectures, how many components, thinking about front-ends and back-ends, will you need to write with the help of an IR? So if you have an IR, an intermediate representation, that is common to all of them, how many do you need to write? Well, how many front-ends do you need to write? How many parsers, Simon?
You would need to, for the whole thing, it'd be M plus N, because you need to write just for each, you have to have one program for each language to convert it into the IR, and then you'd have one program for each language to convert the IR to the backend language.
Exactly. So if you're going to have M languages that you support, you're going to have to write M parsers, just like what we're doing. These parsers that we're writing, you'd have to write M of them. But if you can target an intermediate representation, like if you could target an AST, then if all of them move to the same AST, then what you can do is you can then translate your AST into N different target architectures. So yeah, you would need to write M plus N different components. What if you didn't have an IR? What if you didn't have this stop along the way? How many do you have to write then? Well, yeah, so you need to parse M of them, but then after you parse them, you have to turn them into their backend. So for every parser, you need a backend. So it ends up being M times N. You're essentially making M times N different compilers. And yeah, we've kind of decided in modern compilers, in fact, even way back, that that's not a good idea. You really want to do this separation where you have the front end, the middle layer, and the back end. And what that means is as long as you can write a parser and as long as you can get languages to the same intermediate representation, you can then take advantage of all the goodies in that intermediate representation and then just plug into all the different architectures that that intermediate representation targets. So it's a very useful design with compilers. Any questions on that? Yep.
So you're basically saying that between
Yeah, if you wanted to just make a parser for C and Python, although Python ends up being very difficult because it's a dynamic language. But if you did, and if you targeted the same intermediate representation, then that's all you'd really have to do, because then you could just target the backends with that intermediate representation. And LLVM is a big one there, because what people do now is they just write a compiler that targets LLVM, and then LLVM can target x86. It can target ARM, which is what your MacBooks have. It can target RISC-V. And so all what you have to do is really just make a parser from your language into LLVM. And that's one reason why LLVM is such a cool thing right now. Yeah?
Do you know, is it common for maybe if you want to write something like a super crazy optimized compiler, is it common to kind of get rid of this whole front-end IR back-end thing and just kind of is this approach still used a lot, even in higher performance sort of things?
It seems like, from what I can see, most of the time we still have this. When you said that, the thing that comes to my mind is NVIDIA GPUs, because they kind of have CUDA, and then they just target their own GPUs. But they actually have an IR as well. They have PTX, which is NVIDIA's IR. So they're more of a vertical stack. Nobody else is going to target PTX, and there's not going to be any other backend for PTX. But really, you just end up sticking to this sort of intermediate representation. But you're right, because what you're going to lose is if you have to target, if you have to make your language adhere to this intermediate representation, you might not be able to take advantage of all the goodies that maybe you bake into your programming language, or maybe that your architecture has, because you're going to lose information here. For example, maybe you have for loops, and maybe your intermediate representation doesn't handle for loops. And for loops are very, they're very good to optimize. And if your intermediate language can't handle for loops, then you're losing that optimization strategy or optimization opportunity. So as always, there's trade-offs. But it tends to be that most major compilers have kind of stuck to this intermediate representation architecture. Good question. All right. Speaking of optimizing for loops, loop unrolling will blank loop overhead and blank program code size. So what does loop unrolling do to program code size? Does it make it smaller? Does it make it bigger? Yeah, it makes it bigger. And what does it do to the loop overhead? Reduces it. Yeah. So remember, we had this example here. What is loop unrolling? It's when you have a for loop like this, and what you say is I know that I'm going around an even number of times, so I'm going to tuck in an I equals I plus 1, and then do x equals x plus 1. What that does is it essentially does two loop bodies at once without doing the check. And we can do this because we know we go around the loop at least an even number of times, so we can put two loop bodies here. If you can show that you go around the loop 3 times, then you can put 3 loop bodies here. 102 is divisible by 3, so we could actually do I equals I plus 1 and x equals x plus 1. And then we get rid of another comparison. We basically cut down the comparisons we are doing by a factor of 3. But what are we doing to the code size? This is getting bigger and bigger. Does code size matter? When you're optimizing your program, do you ever think about making your code size smaller, or is that not something we think about, really? You think about making it smaller? Yeah. What do people think? Yep.
I mean, I see the benefit in trying to conserve space, especially I don't know, maybe you want to ship something to customers and they don't want to have to wait an hour to download it.
Mm-hmm.
Your code is massive. But I feel like wouldn't it be more relevant to focus on memory efficiency management there instead of your actual programs code size?
Yeah. So I think that's a really good point. So a lot of the programs that we write here in university, and probably a lot of the type that you will write throughout your career, you don't really have to worry about code size too much. We have a lot of memory in our machines these days, and the code size ends up being not a very big deal, especially to these big data science applications where Yeah, it's actually the data that's big. There is one of probably the most economical important problems, though, that does rely on code size. And that's these big data centers, Google, what they do with search. When you type something in and it has to go and fetch things, or when you run a program like on Google Cloud or in the cloud, in those cases, you're sharing machines with a lot of people, and a lot of people want to run their programs. And what happens is you actually end up with tons of programs, and you end up missing, you end up overflowing memory with your program, and you can actually end up slowing things down. So Google folks, the folks that work on cloud infrastructure, what they'll say, I'm not too worried about end-to-end performance, but I want my code to be very small because I want to fit as much of it in memory as possible because I'm servicing so many people who are sharing these machines. So yeah, compilers have these trade-offs. A lot of times, like I said, we think about making code faster, and that's, makes a lot of sense. But there are cases where code size is also very important. And, would save Google a ton of money if you could reduce the code size, some of this. Yep.
Are there any problems if we, instead of having multiple increment by ones, we increment by value larger than one?
Like if we did in the loop?
Yeah, if we did in the loop, for example, like x is equal to like x plus 2 or x plus 3, instead of having the additional assignments, I guess.
Yeah. So if this was plus equals 2, then we'd.
Sorry, I mean like in the body of the.
Oh, you're saying can we just fuse this to like I equals I plus 3, something like that?
Yeah.
And then just delete those?
Yes.
Yes. Oops. I think we delete that one. Yeah, something like that. No, and this is a case where we can have our cake and eat it too, because that code size increases and then we can shrink it down again. I would say that that's a different compiler optimization pass, and we're going to talk about that later this quarter. But yes, so that's the perfect solution. If you can, and that's why in the compiler architecture, if you remember, we loop on optimizations. It's not just one optimization. So typically you'll have your first optimization might blow your code up like this by unrolling a bunch of loops, and your second optimization might go and then combine those additions. Because it's more obvious that you can combine those additions once it's been unrolled. So you just do this thing in steps. Yeah, good question. Anyone else? Okay, let's take this back a little bit. Okay, the last question. Are there any intermediate representations that you've seen in real life? And if you've not seen or used any, are there any that you might be using without knowing? What do people think? Yep.
Maybe Arnhem is right, but I thought maybe like when I would think of a stack, like I would write something and then push it onto the stack, and then the stack there is doing whatever. It's kind of abstracted for me.
Yeah, that's a really interesting point, and it doesn't. You don't have to think too, or you don't. Yeah, you don't have to squint very hard before you start seeing APIs as sort of an intermediate representation, like using an API like a stack or a container or something like that. Because what they really do is they really just enhance your language with something new and something complex that you use, and then all the complexity is hidden behind the scenes. And intermediate representations are similar. I would also say an API like a stack almost, and we're going to talk about types later on in this lecture. So they do expand the compiler and the language in interesting ways. Yep.
Java bytecode.
Yeah, exactly. Java bytecode's a big one. For those of you who program in Java, hopefully everybody has done that a little bit. Java code is not compiled to the machine code, or at least not directly. Instead, it's compiled to Java bytecode, which is sort of this intermediate form, and then the runtime can make decisions later. Sometimes it moves some of that to machine code. Sometimes it keeps it as Java bytecode, something called just-in-time compilation. It's pretty interesting. But yeah, Java bytecode is this intermediate representation that you use when you use Java. So yeah, Cameron?
So I was kind of interested about this, but I think the answer is everyone in the room has seen an intermediate language.
Oh yeah,
Because some languages target C as their intermediate language.
Yes.
Very interesting.
Yeah, do you have any examples?
I think, I didn't know this stuff when I was just looking it up. I think
Mhm.
All something like I haven't even heard of before.
Sure. Yeah, but you're right. And a lot of times, in your career, if you write a compiler, C makes a very good intermediate representation because you can go to C and then you can just use something like GCC or Clang and get down to whatever bytecode that you want. There's a bunch of machine learning languages where you type in your DNN and then it spits out C code. So yeah, I mean, C is low level. It gives you access to a lot of optimizations. So I think that's a really good point. Yep.
Wouldn't that increase compile time if you're trying to go from intermediate representation to intermediate representation?
Exactly, yes. And so sometimes we end up with these very deep stacks of intermediate representation to other representation to other representation. And GPUs are some of the worst offenders of that. GPUs often have many compilers in their stack. And yeah, it's going to increase compile time. The question is if you do it once and if you execute the code many, many, many times, it hopefully pays off. And think about something like Google Chrome where everybody downloads the binary, everybody runs it. If you spend a long time compiling it to make it better for everybody, it might be worth the cost there. So yeah, it's always a trade-off. All right, anybody else have any questions or comments? Yep.
Just one clarification for that previous question about compiler optimizations.
This one?
Is the compiler literally changing? Like if we're doing loop unrolling and the compiler doing that optimization, is the compiler literally changing the code and then proceeding, or does it happen more at the assembly level?
So it happens in the intermediate representation. So if you have the AST, it's transforming the AST into a new tree. Or if you are in a linear code, which is kind of like something that looks close to assembly, then it's transforming that. It probably is not transforming C and C++ code because that's just a little bit too high level. It's just easier to transform once you move it to something a bit more manageable. And we'll see a lot more examples of that later in the quarter. Yep. And I have this example because loop unrolling does kind of make sense more when you see the C and C++ code, but it's not too bad in an AST. We saw that last time. Joshua?
Is there an example of intermediate representation that's synonymous, like something that we see every day out on the street that could be synonymous to what's going on in the computer?
Well, so you typically don't see the intermediate representations because they're meant to be easy for machines to look at, but not humans. So a lot of times they're hidden. But the one that I think we all like is LLVM. So if you use LLVM, you can pass it the emit LLVM, and for some reason this is massive. Did I do something wrong? Oh, this is GCC. I don't know what GCC does when you ask it to emit LLVM. Let's go to Clang. So this is an intermediate representation. We looked at a little bit of this last time. I would say this is the closest to what I don't know that you see it on the streets, but you use it all the time because you use Clang and stuff like that. But I'd say at this point, it's pretty idiomatic. It's what really captures an intermediate representation because it's fairly close to an assembly language, but it's also kind of far enough away that you can still read it. You get unlimited registers. You have intuitive instructions like load, subtract, floating point subtraction. Yeah, so it's kind of in between what's meant to be read as a human and what the machine can execute. Yep. All right. So let's continue talking about ASTs. So just as a reminder, we were looking at how to implement ASTs. And in this case, we were using object-oriented programming. We were using a little bit of inheritance. We started out with an AST node. You had things like our leafs. So our leaf node is an AST node, and it has a value. And then our leaf nodes can be number nodes, or they can be IDs. That's what we have in C simple. Sometimes you have a binary operator node. Binary operator node has a left child and a right child. And for example, in your binary operator nodes, you could have a plus node or a multiplication node. Not too bad to implement these things. We saw that we can kind of straightforwardly create an AST from a parser. So using these classes, if we have these parser actions that we talked about, in this case we have an expression, a term, and a factor. What we said is, when we run into a leaf, like an ID, you just return an AST ID node. When you run into a num, you just return a number node. And when you just have the parentheses, like we said, the AST doesn't care about parentheses. The parentheses, what they did is they just enforced the certain parse tree that put these operations lower in the tree. So you could just return the AST node for the expression. When you get a multiplication, you can just get an AST multiplication node with your left hand and right hand child. And similarly with plus. So if you have a grammar like this, making an AST is really not too bad. And I think it discusses how to do this in the PLY documentation, as some of you saw. Now, where we have to pay a little bit of attention, though, is that our grammars are not like this. The grammars that we have for our C simple are not left recursive. We said that was a bad deal for us. So what we have to do is we have to learn how to make an AST out of our grammar. So our grammars will look something more like this, where we have an expression. And remember, this is the recipe that you should have applied in homework 2, and you can see in the solution that we gave that comes out with homework 3. So if we just have, this is just a minus example where we just have minus expressions. But in this case, we had to write it as expression is num, followed by expression 2. Expression 2 is minus, num, expression 2, or empty. And if we want to create the parse tree for something like 5 minus 4 minus 3, it ends up looking something like this. And it's really not clear how to make an AST from this directly, because you come down to the bottom, this is the last thing you're going to parse. But if you're down here, you kind of have nothing here because that matches this rule. And then you have a 3 minus. And how do you make an AST out of that? Minus has 2 children. So you need somehow how to complete the AST given this information. So it turns out that if you follow this sort of definition of parser actions, where you kind of just have code that you execute after the entire option is matched, this doesn't really help you make an AST when you have our top-down grammar that's non-left recursive. So we have to do some extra work here. We basically want to get a tree like this to look like this, because this is our AST with minus nodes. We have 5 minus 4 minus 3. And these trees look quite a bit different. So let's think about how we can do that. Now, because we're writing our own parser, keep in mind we're writing our top-down parser, we can really inject code at any point in the parse. And for those of you who have started on homework 3, what you might have noticed is, this is how you're going to do the symbol table. The symbol table, you can basically call it whenever. So because we can introduce code at any point during parsing, that's going to help us transform a tree like this into the tree that we want. So what we're going to do is, as we're parsing this in our recursive descent parser, again, that we're writing by hand, that's what homework 3 is, if we get a number node, we make an AST node for that. That's fine. It's a number. We can make an AST node for that. Then what we have to do is, rather than immediately returning our node, when we go down to expression 2, we have to pass that node down as an argument. Now, this seems a little bit strange, but again, because we wrote our own parser, we can do this. So expression 2 now gets this AST node of 5. We pass it down as an argument. Then what we do is in expression 2, if we pick this rule, minus num expression 2, we can start building more onto that AST. We can say minus 4. So we get that minus, and we get that 4, and now we can make this AST node, because we complete that with a minus 4. Now what we have to do is we have another expression 2. So we need to pass down this root node. We need to keep passing down that root node, and we pass down that AST minus here, and then that gives us a minus 3. So this 3 is going to be the right-hand child, and this minus, that's going to be the node, and then the left-hand child is going to be this minus node there. And so then we end up getting this. So essentially, we need to do a little bit of work. We need to pass an argument down. We need to construct our tree in a slightly different way, but it turns out not to be too bad. For people who like functional programming, there's a functional programming approach that you can use to solve this, but I'll let you think about it and figure it out. What happens now is we pass down that new node, right? We keep passing nodes to expression 2. Expression 2 takes a node, but now we have that root node. This expression 2 is going to match this last rule because there's nothing else to match. And then what you do is you just pass this node all the way back up because you're essentially done making the AST node there. And that expression now returns this AST node. And we've constructed a more classic AST from our parse tree that looks a little bit strange. So if we think about how to implement this in code, again, you'll be doing this for the next homework, not this homework. What you do is you would get a leaf node from your number node. So when you parse an expression, remember, this is how the recursive descent parsers work. How do you parse an expression? Well, you parse a num, then you parse an expression too. So when you parse an expression, you grab your leaf node, and then you pass that node down to expression 2. You give that as an argument. And then when you parse an expression 2, we've now added a left-hand side node as an argument. What are you going to do? You're going to eat the minus. So the minus gets eaten. You're going to make a leaf node number out of number 2. So that gives you your next node. And then what you need to do is you make a new minus node with your left-hand side node and your right-hand side node. And then you keep passing that down to the parse expression 2. And that node then becomes the left-hand side node to your next expression 2. And if you're going to apply this rule where you don't do anything, then you just return that node that was passed down. That's a complete AST node. It's a minus node. You can just return that, and that will bubble its way all the way up to get returned with the expression. So again, we're going over this just a little bit early because you'll be doing this in homework 4. But what this essentially means is when you're writing your own parser, if your parse tree doesn't look like your AST needs to look, you can always kind of massage it and return things, add arguments, and eventually get an AST that looks more idiomatic. Yep.
Okay, wait, just to clarify, eat means so it checks the token right now, and then it will advance it.
Eat.
Does it advance
Yep.
it first and then checks it?
Let's see. You need to be keeping track of the next one that you want to match. So when you eat, you basically say, what was I looking at? What was the scanner looking at? So there's got to be some member variable that you're keeping track of that. And then you say, I'm seeing a num. The next token that I needed to match better be a num. And then you advance it with s.token. I mean, I guess you could advance it first, but I just kind of see it as more logical to check that you saw the thing that you wanted to and then advance it. Yep. Okay. So there's some implementation details. But I think the interesting thing here is, again, to note some of the differences between an AST and a parse tree. Remember, what we said is when you have those, what you might call a natural parse tree, the parse trees that we've seen before, you can really evaluate them in a post-order traversal. So just, traverse all the children, then evaluate the node, and that's kind of how you evaluate them. When you have a parse tree like this, like we are going to have in our grammars, you don't really evaluate them in a post-order way. It doesn't really make sense, right? You do 5, you come down here, like essentially you'd be trying to evaluate -3, but then what do you -3 from? It doesn't make a lot of sense. But an AST, if you have an AST, one property of an AST is that you should always be able to evaluate it doing a post-order traversal. You need to come down here, evaluate this node, which means 5 minus 4 is 1, minus 3 is -2. So yeah, the grammar that we have isn't really evaluated in a post-order way, and we need to turn it to a parse or an AST that is evaluated in a post-order traversal. All right, does that make sense to people? And like hopefully now you can see there's decisions that you make when we decide which parser to write. What we're going to find is that we can write a recursive descent parser using a grammar like this, and writing the parser itself actually isn't too bad. But what we had to do is we had to massage the grammar to get it into a non-left recursive way, and there's a little bit of extra work in building the parse tree. The other option is that you do a bottom-up parser, and we're not going to talk about that in class because that would be like a week and a half of just deriving the algorithm on the whiteboard. But you can read about it in the book, and if you do something like that, then your AST is just much easier to make. It's like what we saw before with the ply. So, trade-offs as always. What's nice about Python, though, again, with these ASTs, you can go see them for a lot of the code that we know and love. Python has an AST module. You can import AST, and you can do an AST of, you can dump it of any Python code you want, really, and you could say something like 5 minus 4 minus 2, and it would give you essentially an AST that's flattened like this. You can see that it's a subtraction where the right is num2. Let's see. So the first one is a binary op where the left is num5, subtraction, right is n4, and then after that you subtract n2. These things are always kind of a pain to read, but this is really just a flattened tree, and you can go see the types of ASTs that Python will give you if you want to go play with the Python module. Okay, so like we were saying, one property of an AST that is really foundational to it is that you need to be able to evaluate it in a post-order traversal. So if you had something like x minus y minus z, you can't really evaluate it. These could be variables. We don't know what they are. In the past, we've been looking at numbers because it's intuitive to see numbers and think about how it's evaluated. What do you do in this case if you can't evaluate it? Well, now you actually need to implement, or you need to produce binary code. You need to actually write code that gets executed. Compilers can't arbitrarily compute all of your code for you. But I want you to think about something a little bit different. What if I start to add types here? What if I say x is an int, y is an int, z is a float, and w is a float? What happens to this expression now? Does anybody know? Does this compile, first off? Or are we able to compile this? Yeah, who says yes? Okay, anybody say no? Yeah, Jacob says no. Why? Yeah, what do you think? Okay. Yeah, semicolon at the end, yes. You've been writing enough parsers. I can see that. Okay, so with the semicolon at the end. So this feels a little bit weird, though, right? Because we're combining, like floats and ints are different, but we're doing math on both of them. What ends up happening here? Yep.
I would guess that the ints get demoted to floats.
Would you say demoted or promoted?
I would say demoted.
You'd say demoted. Yeah. Fair enough. Why wouldn't the floats get promoted to ints?
I guess I'm not really sure. I guess it comes from what a float is, which is an approximation.
Okay.
I don't know exactly.
Yeah. But you're thinking along the right path. Something has to change, and yeah.
They get converted to a float.
Converted. Yes, that's a good word, and yes, you're exactly right. So that's what we're going to be doing.
And that's what most languages do anyway. So that's what's doing.
Yeah. Is there any, so that's exactly right. We need to convert it, and every language is a little bit different with these rules that it does. But let's go plug this into Godbolt and see what happens. So let's see. Let's go over here. Actually, I have it just right here. We're passing in int x, int y, float z, and we're returning the value. So first off, what we know about this is subtraction is left associative, right? So we're going to do the, we're going to do the x minus y first. And x and y, those are ints. So does anything really need to change here? Yeah. So you can go to the intermediate representation, and we kind of have to do some mapping by looking at it, but there's a sub here, and this is an integer subtraction. So yes, the first thing we do is an integer subtraction. Then we have this strange instruction, sit of p. Let's see if we can get some documentation. Come on. Do we get documentation? If we don't get documentation, that does exactly what you said. It converts the integer to a floating point. So I'm guessing this signed int to floating point. That's got to be what it is. And then what we get over there is that gets converted, and now we have a different subtraction. We have f sub, a floating point sub, to then do the subtraction of z. So, this isn't magic. The compiler is doing this, and the compiler is tracking the types, and it's determining when it needs to convert and when it needs to use the different operations. Camden?
What if the return type was int?
Okay, good question. Yeah, what would happen then? Does anybody know? Like, first off, would it compile? Who says yes? Okay, who says no? Some people, not sure. Let's try it. Int. Interesting. So it does compile. And when something compiles, as long as we don't have any undefined behavior, that means there are specific rules for what needs to happen. And if you come down here, we have another one of these strange alphabet soup instructions, fp to si, which, if our hypothesis is right, it's floating point to signed integer, and it's doing that before it returns it. So that's really interesting, Camden, because first, after we did this, we converted it to a floating point, but then we just convert it back to an integer when we return it. Yeah, so kind of interesting, right? Well, let's think about, yeah?
When it turns into actual assembly, is there like a function or a macro that they use to convert the floating point to the integer?
Yes, there is a special assembly instruction that does convert the bitwise, and that's exactly kind of what we're going to talk about next. So, well, we're going to have these in our intermediate representation, and then yes, the architecture will have to do that. So, and that's actually just leading into the next part of the lecture. Why do we have two different subtract instructions? There's sub here and there's f sub here. Why do we need that? Like, can't we just, when we write Python, when we write C, we just say subtraction. Can't it just do subtraction? Why do we need two of them? Naomi? Well, yes. For those of you who haven't taken architecture, when you subtract integers, that's different hardware than what subtracts floating points. When you multiply these numbers together, floating point has the IEEE specification. It's weird. It has this mantissa bit, precision bits, and stuff like that. But it's different hardware that does arithmetic on these things. But your hardware really doesn't care about the type. It will take any bits, and it will operate on whatever bits you give it. So, and we can actually see this if we just output assembly. Let's see if we have here. I see a subtraction here, and I see a subtraction there. Let's go to x86, because I know x86 a little bit better here. So if you go to x86, we have sub, this is an integer subtraction, and we have a sub SS, which is the single precision floating point sub. So exactly what Naomi said. We have different hardware, and that hardware the hardware expects different bit representations of the operands. If you are subtracting an integer, then you can, you just have binary numbers like we know and love. If you are subtracting single precision, it is expecting IEEE floating point format. And so that's why you need to do these conversions. And like you were saying, here's our converts a signed integer to single precision, and here's converting it back. So there are assembly instructions that do this. Okay. So, like we said, this one needs to be a sub instruction. This one needs to be a sub SS. And right now, with the AST in the form that we have, we don't know that. These are just subtraction nodes. We need to make this a little bit more specific. And yeah, furthermore, if we look and think about why this needs to be more specific, if we do like 5 minus 5.0, like in Python, what do we expect this to be? 0.0. So yes, we at least expect it to be some representation of 0. But let's see. Actually, this should be sub. So if you do sub SS, here, and if these two are stored in R1 and R2 as registers, it's going to interpret both of these as floating point. So 5.0 has some floating point representation, but if we look at the binary for 5, it's 101. And not too difficult. But if you interpret 101 as a floating point number, it ends up being 7 point something to the negative 45, essentially 0. So what we need to do is we essentially need to convert this bit representation of 5 to the floating point representation of 5 before we do this subtraction. And the compiler is in charge of essentially inserting those instructions and making sure that these type conversions do what they're supposed to do. I guess that leads to kind of a philosophical question. What are they supposed to do? What is a type conversion supposed to do for us?
Convert types.
Yes, exactly. Well, should it always, though?
No.
Yeah, so somebody a long time ago, when they made C, said that we're going to automatically convert ints to floats. A lot of people have stubbed their toe, shot themselves in the foot with that, because when you convert an int to a float, it becomes an approximation. It's not great. So other languages, especially functional languages, they don't automatically convert it for you. They say, if you want to convert it, I'm going to force you to do the conversion yourself. And as a programmer, it can feel very annoying, but you have to make it explicit. So, what should the compiler do here for type conversions? It does whatever the programming language says it's supposed to do, and there are many design decisions that you can make here. So, what we need to do is, after we have our AST, we need to refine it. We need to transform it to deal with types. And in particular, we need to make an int to float node so that you can have, this is going to be an int. It needs to transform to a float before it makes it here. So, to do that, we're going to talk about type systems. And this is going to be a very limited view of type systems. Type systems is this big area in computer science that people have done so much work in. We're barely going to scratch the surface. But, at a high level, a type system is given a language type system. So a language defines a type system. What that needs to provide is the primitive base types in the language, how the types can be converted to other types, and that can either happen implicitly, like with those floating points and ints that we saw, or explicitly. And the type system should additionally talk about how the user can define new types. So that's what a type system is. When you have a type system, the compiler typically performs what's called type checking and type inference. This checks a program to make sure that it adheres to the type system, and it inserts any automatic conversions that need to happen. And essentially what this does is it prepares the language to be translated to a different language that has a different type system. Because binary has a different type system than C. And so, we need to essentially get our types in order so that we can continue translating it down. And so there are different types of type systems for languages. On top of the actual types that are implemented, there's kind of higher level type system properties. For example, we have statically typed languages. In a statically typed language, these are types that can be determined at compile time. So this is something like C. We have to tell the compiler what types they are, right? We have to have int x, int y, stuff like that. But we are at least telling the compiler, and the compiler will go through and make sure that when you use x, you're using it in a way that ints can be used. If you have a float f, and if you use f, it makes sure that you're using f in a way that floating point numbers can be used. And the compiler knows what types they are so they can check them. It's kind of interesting because it's also related to the auto keyword in C++. Who uses auto in C++? few people. Yeah, auto is essentially a way that says, I'm not going to give you the type, but you should be able to figure it out automatically. And the compiler generally is able to do a decent job. But before auto, which wasn't really supported widely until 2015 or 16, all types you needed to declare them. Additionally, you have dynamic languages like Python. in these languages, the types are determined at runtime. You can say x is equal to 5, and then you can say x is equal to hello world. And you can change the types however you want. And you can't really determine what they are until the runtime. And then you have untyped languages. Untyped languages essentially means that the language has no types in it. You just need to make sure that the binary representation matches whatever hardware unit you're passing it to. So let's talk about some pros and cons of each. So if we have a statically typed language like C, one of the benefits is that the compiler underneath the hood knows exactly which assembly instruction that it needs to do. We saw in x86 that you have like add and then you have add ss. Add works for ints, add ss works for floats. If you don't know what the type is, then the compiler has to emit code that basically says, hey, if you're doing x plus y, you have to check if they're both ints. If they're both ints, then you can use add. And if one of them is an int and one of them is a float, you have to convert that int to a float, and then you can do an add ss. So if the compiler cannot determine what the types are at runtime, you essentially need to have this overhead. You can't escape it. It's one reason why Python is slower than C, because basically every time before you do an operation, you have to check what type it is and make sure that you're going to the right place in hardware. So statically typed languages can be very fast. Dynamic languages like Python, right?
Would that overhead have to work recursively to try and I guess that would just happen in the recursive process when solving the equation?
Yeah, you'd have to go through every single sub-expression. And essentially, we're going to talk about type inference, and it's a recursive process, and it essentially has to do it for every single operation. Yes. When we have dynamic languages like Python, I love Python, and you can write really generic code. You can say add x and y that returns x plus y. This is simpler than what we all probably do, but I don't have to tell it that these are ints. I don't have to tell it that these are floats. These could be lists. These could be strings. And I just have to write this once. Now, I end up having lots of bugs in my code, but you can write pretty generic code, and things it can actually work out quite nicely. But the compiler, because it doesn't know what types these are, when it executes it, it has to check. It has to, before it executes x plus y, it has to know what type they are, and that checking causes overhead. Then untyped, what we mean by untyped is essentially assembly. You can write really optimized code because you know exactly the functional units that you're going to pass this to. Are you going to go to an integer addition unit? Are we going to go to a floating point addition unit? It's very painful, and there are many, many bugs. And so we will be compiling to an untyped language in this class. And so we'll get to see some bits and how they behave. Okay, let's talk about some considerations of type systems. So a lot of times, it's kind of hard to really come up with something generic, but a lot of base types that we see like ints, we see characters, we see strings, we see floats, we see booleans, right? And then what type systems need to do is they need to be able to tell us how to combine these types and expressions. So we kind of talked about this before, but what happens if you add an int and a float together? Yeah, let's try it out, actually. We have Python here. Let's add an int to a float. Our answer, this looks like a float, so it's going to be a float. What happens if you add an int to a character? You guys sure? Python gives us an error.
Oh, because all of them are strings.
Try JavaScript? Oh, no, I won't. But I will go and we can try, let's say I found this online C thing that will execute our C code. So this is C++. Let's try here. Let's standard out, and let's do a plus 5, and we can execute this. And it compiles, and we get 102. So in C, you can combine characters and ints. In Python, you can't. So already you can start to see some rules that we're coming up with. What about an int and a bool? Does anybody know?
+1 int.
Yeah, what happens if we do 1 plus true? 2. What about 1 plus false? 1. What about...
False plus true.
Yeah, let's try that. True, what's that? Wait, it's an indent. 1, okay. Yeah, so you can combine these. And what's interesting, what I find interesting about like the bools is like true plus true is you sort of leave the realm of bools. Like 2 isn't a bool, but if you add 2 bools together, you don't get a bool, you get an integer. So it's kind of weird. That's what I would think, but I didn't invent the language. Okay, so what happens in C++? Can you do this? Can you do true plus true? 2, yeah. False plus true. So you can see that we can combine them. Camden?
I just wanted to point out a cool little trick you can do is like if you have a character, you can subtract it from its character 0 and you get the integer for the character as a number.
Wait, really? So
Character 5,
what if you do that?
the character 0, you should get the integer 5.
Yeah, in C. Oh, interesting. Okay, so if we do something like... Yeah, let's see. Plus. So if I do subtract, what does that give us, Camden?
Maybe you can do like 5, like the character 5 minus
Oh,
the integer 5.
5 minus 0. 5. Hey, cool. I didn't know. But yeah, all this stuff comes out of the type systems. And, type systems, they also get interesting when we have things like strings. Like strings and pointers get pretty bizarre. Like what if we had like AA plus 2? Can we do that in C++? We can somehow. I didn't think we could. Okay, you can do AA plus 2. What about AA times 2? Nope, there's an error there. So we can add to strings. Interesting. Why can we add to strings? I actually kind of figured it out in my head. Elliot? Oh, well, almost. Python's going to give us concatenation. Do we concatenate strings in C++? Let's see. C++ doesn't like concat. Okay. See, strings are weird. So we could add to it, but, we could add an integer to it. Okay, so this is what I think. I'm coming up with this on the spot. This is just a pointer. This is an array. And you can add to pointers in C. So we can do that. In Python, though, you can concatenate strings. Can we add to strings like we can in C? No. Can we multiply strings in Python? Yes. So now we're starting to see that these languages that feel kind of similar, when we start combining types, they start to behave a little bit strangely. Joshua?
Briefly going back to Booleans, am I mistaken, but if it's any number that's not 0, be considered true?
I think so. I mean, that's how it's evaluated in a conditional. But for example, if you said true is 5, you'd get false. So I think true is interpreted as a 1, but then if you're in a conditional and if you're trying to see if something's true, then it's anything non-zero ends up being true. Yeah, so tricky stuff. So we get some really interesting things when we try to combine types. And pointers are very strange as well. We can add to pointers, we cannot multiply by them. I'd suggest go try combining some of your favorite types and see what happens. Sometimes you might be surprised. So we're seeing that languages behave different with types. Some of them, some things are nice and intuitive. Some of them are a bit weird. So we looked at that. And so let's see, I think we'll get to it by today. So in type checking, what we're going to do is we have 2 components. We're first going to do type inference. And type inference determines a type for each AST node. So in the past when we saw our AST nodes, it was like this was a subtraction, this was a number. Now we're going to add a type to them. And then what we have to do is after we add the types to them, we need to modify the AST so that it's in a type-safe form. So here, what are we going to do? Well, we need to add a type to each of these nodes. For these IDs, we know what type these IDs are because the user has told us. The user says X and Y are ints, Z and W are floats. So we can just add a type to those leaf nodes. Then what we do is we need to get the type for these middle nodes. With these middle nodes, what you do is you end up with these tables. we have a decent number of tables in this class, but these tables are the inference rules for addition. And what the inference rules say is if your first child is an int and if your second child is an int, then your result is going to be an int. But they also talk about how to combine types. They say if your first child is a float or an int and the other one is a float, then you're a float. In fact, if any of your children are a float, then promote it to a float. So this one, we just look int, int. Our table tells us that that is an int. Now when we go to the top, we say, what is this one? Well, we have an int and a float. So we go and look in our table, and now we have an int and a float, and our result is a float. So essentially what we're going to have is we're going to have these tables. Now, these tables do follow patterns, and there are some intuitive things about these tables, but there are also some weird things with them. And so I don't know that we have time to get into it today, so let's leave it at that for today. So go study for the midterm, and I'll see everybody on Wednesday. Good luck. You're going to do great, and enjoy your weekend.